So let's uh, start today's lecture. Am I audible?
Yes.
Okay. So, uh, so let's start with my introduction. My name is Harini. I'm a PhD scholar from Interdisciplinary Center for Water Research at Indian Institute of Science, Bangalore. So, currently I'm doing PMRF TATUT for the course Watershed Hydrology offered in NPTEL by Professor Rajendra Singh from IIT Kharagpur. So, this session, we will be talking about types of abstractions that occur in hydrological processes. And if you have any doubt, you can ask me during the lecture itself, wherever you have doubt, or if you have any other doubts regarding the this week's topic, then you can just raise the hand and ask me the questions. So, coming to abstraction, what does it come to your mind when you hear the word abstraction? It means generally we say that if there is any loss in the system, we call that as abstraction. So, in previous lecture, we have talked about hydrological cycle. So, now when we are talking about abstraction within hydrological cycle, we are talking about any process which will remove the water from the hydrological cycle or in the watershed either by natural or artificial actions. So that is, suppose if in this case, if we are taking if we are talking about hydrological cycle, we have precipitation, which will be an input of rainfall, and we can see there is an evaporation occurring. That is, this is taking the water out of the system. So evaporation is one type of abstraction that is occurring, and also you can see that water is getting stored in the depressions. This is the another type of abstraction that is occurring. And also we experience interception losses, which are like which is due to the adherence between the water molecule and the object that the water molecule comes into contact. So also we have transpiration, which is another loss that occurs from the system. So all these are the four types of abstractions that occur within the hydrological cycle. So now I'll just write down the definition of abstraction. So abstraction is a process by which water is removed from the natural hydrological cycle or watershed, either naturally or by human activities. Okay. So the major types of abstractions that we have talked about are: first one is interception loss, second one is depression storage, third one is evaporation or transpiration. Okay. And also major abstraction that occurs within hydrological cycle is infiltration. So when the water that falls on the soil gets seeped into soil, this is called as infiltration. This is a major loss that occurs within a hydrological cycle. So as I have told you about, first let's talk about interception. Okay. So what does interception means? So as I have told that whenever water molecules come into contact with any other object like leaves or trees or buildings, they get ethered due to adherence. They get stick to the surface. This is called as interception loss. So now coming to the types of interception losses that occur. So we can see that whenever the rainfall falls, the first thing that the water comes into contact will be either the trees or the buildings. So currently we will be talking about the interception losses that occur in the vegetation part. So whenever they first the water will touch leaves or the canopy of the tree, right? So the major interception loss occurs in the canopy of the tree part. This is called as canopy or crown interception loss. And then from the leaves, the water will fall onto the ground surface. This is called as through fall. So also from the leaves and branches of the trees, the water will slowly pass down to the ground surface through the stem, right? Main branch of the tree. This is called as stem flow. And when they finally reach the soil, due to the leaves and everything that is on the ground surface, the water will get accumulated there, and due to evaporation it will get evaporated, right? So whatever the loss that is occurring on the surface of the earth in forest cover is called as forest floor or litter interception loss. Okay, so now we have discussed about majorly two types of interception loss. That is, first one is canopy or crown interception loss, and the second one is forest floor interception loss. So do you have any doubts in these two sections? So now that we have understood what is interception loss and what are the types of interception loss, so now to estimate the interception loss, what we will do is like we'll first try to calculate crown interception loss. So this is calculated using by taking multiple rain gauges. Okay, so crown interception loss is equal to Rg minus Rt minus Rs. So here Rg represents the rain gauge, rain gauge located in nearby openings. That is whatever the amount of water rainfall collected in the rain gauges that is located in the openings is recorded in this rain gauge, and RT represents the rain gauge that is under the canopy. Okay, and RS represents the um, the collars under the stem. That is, we will keep collars around the main branch of the tree, and whatever the water is getting collected is because of the stem flow that is occurring. So from the main precipitation, if we gross precipitation, if we remove the through fall and stem flow, then we will get crown interception loss. Okay. So now the second interception loss is forest floor interception loss. So how do we calculate this? So this is just by experimental method. So what we will do in this method is that we will collect the sample of litter that is in the forest floor, and once the we'll take it when it is completely wet, and we will dry it out and weigh the sample before and after. The difference of the weights is called as will give us the interception loss. Okay, so generally the interception loss. will account to only 3 to 5% of total precipitation. So it is a very minor loss, but in most of the cases, we will consider the interception loss as negligible. So, but in few in agricultural engineering, it is very important to estimate it because we will be working in agricultural fields or forest area side. So that's why to estimate it, we have like mathematical models as well. So the mathematical model, we have three mathematical models that are discussed in the class. So the first one is Jensen model, which is given in 1983. So here we will calculate the maximum storage capacity is equal to C into leaf area index. So C in is interception parameter, which is approximately equal to 0.05, and this is leaf area index. So leaf area index is the amount of area, the total area that the leaves are exposed. Suppose when we are suppose we have 100 leaves for the canopy, then you will have an area for each leaf, right? Based on that, we will estimate the leaf area index. Okay. So here we are considering that infiltration is a function of vegetation type and stage of development. Okay. So, and the second model is Horton model, which was proposed in 1919. So here we will be calculating the volume of water intercepted, Li equal to S plus KET. Volume of water intercepted. Okay. And S here represents the interception storage. Okay. K is the ratio of surface area of leaves to the area of entire canopy, and E is evaporation rate, and T is time. Okay. So using that we can find the volume of the water intercepted. So in this case what we are trying to do is we can see the term time is also included. So that means if the duration of the storm is longer, then we can expect more evaporation that will occur from the canopy. So that's why we can say that more water can be intercepted. And also we can see that the function is also depends on the interception loss also depends on the season, because uh, the deciduous trees lose much of their canopy storage potential during winter months than in summer months. So we can see that the interception loss also changes with season in this formula. So the third model is, sorry, Mariam model, proposed in 1960. So here we'll calculate the interception loss. I is equal to S into 1 minus exponential power minus P by S plus Et. So here S is the interception storage and P is the gross precipitation. E is the evaporation rate that occurred during the precipitation event, and T is the duration of event. So from these three models, we can find the rate of we can find the infiltration loss that occurs within a watershed. Also, one more important point that I would like to highlight is that interception loss is always a function of what is the vegetation type that we have and the stage of growth of vegetation and the intensity of precipitation, duration of precipitation, also the type of precipitation and frequency. So it depends on the characteristics of the precipitation as well. Okay. So till now we have discussed about the interception loss, the types of interception loss, and also how we can estimate it. Now let's come to the second type of abstraction, that is depression storage. So what is depression storage? So whenever there are depressions in the land surface, so water will get accumulated in those depressions. Okay. So once they get accumulated in that, till they reach the outer upper limit of the depression, they can't come out. So whatever water gets stored in the depression will get evaporated. So this is also a type of abstraction that occurs within the catchment. So the definition for depression storage is water that drains into closed depressions and never reaches the outlet of the basin. So whatever water is getting stored in the depression will either get evaporated or get infiltrated into the ground. Right. So now let's talk about what are the methods that we can use to estimate this depression loss and depression storage. So for estimation, we can go with using hydrological budget, water budget. Okay. So here we have depression storage term on the left hand side. So this can be equal to, we have an input rainfall. So from that we have to remove runoff, infiltration, evaporation, and interception. So once we remove all these terms from the rainfall, then we will get the amount of water that is stored in the depression. Okay. So we can also use some mathematical models like Lindsley proposed in 1949. Here they have given an equation saying that of volume of water stored at time t. V equal to St into 1 minus e power k into ep. Right. So here SD is the maximum depression storage capacity of the catchment. So maximum depression storage capacity of the catchment is SD, and we have PE is excess rainfall, which we will be talking about that in later class, and K is the constant. K is equal to 1 by SD. Okay, so here we can see that if PE becomes very large value, then the volume of water stored in the catchment will equal to the maximum storage capacity of the depression within the catchment. If PE is approximately 0, then the water stored in the depressions will be 0. So we can say that V value ranges from 0 to SD. So how do you think we can estimate the maximum depression storage capacity? So from like topographical maps, we can estimate the depression storage capacity of a catchment, or by field measurements, we can calculate the depression storage capacity. Okay. Now let's look into the few of the questions related to this topic. So the first question is, which of the following surface will have the most pronounced interception? So first option is paved roads, second option bare soil, third option dense forest canopy, option D is concrete buildings. Any guesses? So the answer is dense forest canopy. So as we have discussed, most of the interception loss that in will occur in forest areas. So the answer is dense forest canopy. The next question is, interception loss is not a function of which of the following factors? Option 1, leaf area index. Option 2 is precipitation intensity. Option 3 is precipitation frequency. Option 4 is soil type. So when we have talked about interception loss, we are mainly concentrating on the characteristics of the precipitation event, like the intensity, frequency, duration, and the type of the precipitation event. And also we were talking about the vegetation type, or also the stage of development, so which will be covered in leaf area index. So the answer is option 4, option D, soil type. So now coming to next question. Here we have a problem where it's asked to calculate the interception loss using the Merriam model for the rainfall event with the storage capacity of the basin equal to 5 mm, precipitation to 12 mm, and evaporation, that is occurring rate of evaporation is 0.8 mm per hour, and duration of the storm event is 4 hours. Okay, so we have seen that the formula for Merriam model is I equal to S into 1 minus e power minus p by s plus et. So once we substitute all these terms, we have 5 into e power minus 12 by 5 plus 0.8 into 4. So Now, by using the calculator, so the answer is 7.746 mm, right? So the answer is C. Here we have to estimate the interception loss in mm. Okay. Um, so now let's talk about other abstractions that occur in the hydrological cycle. Okay. So the next important abstraction that occur within hydrological cycle is evaporation. So we have heard about what is evaporation lot of times. So evaporation means the liquid water will get converted into water vapor by transfer of water molecules to atmosphere. Right? Generally, in most of the cases, the evaporation that occur between the rainfall and runoff event, we consider that the evaporation rate is negligible. But between two runoff events, the evaporation is a huge value. So we will not neglect the evaporation that occurs between a runoff event. So also when we are modeling the hydrological events, we have two type of hydrological models basically that we look into: event based or continuous based. So in continuous uh, models, we will never neglect the evaporation term, but in event based models we can neglect the evaporation term. Okay, so I'll just highlight that. Evaporation is not neglected between runoff events and also in continuous hydrological models. So now let's look into what are the factors that affect evaporation. So if you have heard about, if you have listened to the week 2 lecture, you might have seen lot of factors that affect the evaporation rate. So first factor is vapor pressure. So in this, we consider the Dalton's law. So evaporation rate is equal to constant into vapor pressure at the water temperature, and A is the vapor pressure of actual vapor pressure in air. Okay. So when vapor pressure So when saturated vapor pressure at water temperature is equal to actual vapor pressure, then there won't be any evaporation that will be occurring. Okay. So the second factor is wind speed. So as the wind speed increases, the evaporation rate increases, because when wind flows, the water molecules above the water bodies will get drifted away. So it will give us chance for the water to get evaporated, more water to get evaporated. Okay. Then the third factor is air and wind temperature. So this is basic thing that we know that as the temperature increases, evaporation rate increases. Here I am considering E as evaporation rate. Okay. So then the next factor is size of the water body. So as the size of the water body increases, we will have lot of water that is exposed to the atmosphere, right? So more water will get evaporated. So evaporation rate increases. Then the fifth factor is atmospheric pressure. So as atmospheric pressure decreases, evaporation rate increases. So because it's easy to reach that vapor pressure, so then the evaporation rate increases. Okay. And if the water is not pure, that is, if it has some soluble salts or anything, what will happen is the vapor pressure of the uh, water with soluble salts decreases. This implies if the vapor pressure decreases, the evaporation rate increases because of this formula, right? So that's why in sea and oceans, we see 2 to 3% less evaporation compared to freshwater bodies. Okay. So is this clear? In this slide, we are talking about how does evaporation occur, and when we don't neglect evaporation term in hydrological processes, and also what are the factors that are affecting hydrological process that are affecting evaporation. So that's why it is important to measure evaporation. So to measure evaporation, we have set up the instruments like pans to calculate the evaporation rate. So we have different pans that are available. So first we will be talking about class A evaporation pan. Okay. So here it's a so it's basically a cylindrical pan, and which is coated with which is made of unpainted galvanized iron sheet. And then what we will do is we'll fill the evaporation pan with water, and we will leave it in the sun in the open space, and we will check the amount of water that has decreased. So we will take measurement at every 8:30 a.m. every day in the morning, and based on the water depth that has reduced, we will say that this much amount of evaporation has occurred. Okay. So it's made of unpainted galvanized iron sheet. The details of this pan, with more details of the pan, is given in the lecture where sir will be talking about the dimensions and how the recording also will they take recording will happen in this pans. So the second one is ISI standard pan. So it is similar to Class A plan, but we have modified for our Indian condition. Modified Class A pan. Okay. So here it is made of copper sheet, and also the is outside of the cylinder is painted white. So once it is painted white, because of the thermal conductance of the copper sheet will reduce because it's painted white. So the evaporation rate also will decrease in ISI standard pan compared to Class A pan. Okay. And we also put wire net on the top surface of the pan to protect the water from animals and birds. In ISI standard plan, we notice that there is 14% lower evaporation rate compared to classic pan. So then the third type of um, pan we have is Colorado sunken pan. So as the name here suggests, the pan is buried inside the earth surface so that the aerodynamic conditions of the pan will match the real-time lake conditions. So, and also this pan is square shaped. The other two are cylindrical shape and made of galvanized and is made of unpainted galvanized iron. Okay, so it is buried like within 100 mm from the ground, and also the so that the aerodynamic and radiation characteristics will be similar to the lake. And now that we are measuring the evaporation rate using the pan, how can we apply it to the how can we find the evaporation rate that occurs in lake? So, because the conditions, environmental conditions, and also the characteristics of lake and pan are completely different, we have to apply some correction factor. So, using pan quotient, what we will do is the lake evaporation is calculated from this measured evaporation rate by multiplying a pan quotient term. So, pan quotient into pan evaporation. This pan evaporation will vary based on the type of pan that we are using. So we have, as we have discussed, we have Class A pan, ISI standard pan, and also Colorado sunken pan. So based on the type of the evaporation pan that we are using, the pan quotient also will vary. So once we multiply with this, the pan evaporation rate, we'll get the lake evaporation that will occur. So also we have like we can, instead of going for measurements, we have other methods also to measure evaporation. That is, first one is water budget. So in water budget, it was proposed by Horton. We will calculate evaporation is equal to inflow plus precipitation minus outflow minus seepage minus change in the storage that occurs in the catchment. So evaporation is equal to inflow, precipitation, outflow, seepage term, subtract, and change in storage within the catchment. So using this one, if we have these values like what is the precipitation occurring within the catchment, outflow, inflow, seepage, and change in storage terms, then we can find the evaporation rate using the water budget equation. So also we have like empirical methods as well. First, in empirical method, we have Mayer's formula, which was proposed in 1915. So, let me write this on next page. So, empirical formulas. First one, we will be talking about Mayer's formula proposed in 1915. So here the lake evaporation rate is equal to quotient into saturated vapor pressure at water temperature minus actual vapor pressure into 1 plus U9. U9 means the wind velocity at 9-meter height. Okay, by 16. So this is a quotient which depends on various factors, and EW is saturated vapor pressure at water temperature. EA is actual vapor pressure, and U9 is wind velocity at 9 meters height. Okay, so this quotient, Km quotient, will be vary based on the depth of water in the lake. So if it is a deep water, then the Km value is 0.36, large deep waters. And in case of shallow small waters, the Km value is 0.5. Okay. So in these terms, we don't know, we have to know how to estimate the saturated vapor pressure, and also if we have wind velocity at one and particular height, how do you calculate wind velocity at like 9-meter height? Okay. So saturated vapor pressure is given as 0.4584 into e power 17.27 into T by 237.3 plus T. Here T is temperature in degrees Celsius. Okay. So, and wind velocity at any height is given by the formula sub constant into h power height in meters power 1 by 7. Okay. Height in meters. This is constant. This is wind velocity in kilometer per hour. Okay. So using these formulas, we will find the saturated vapor pressure, actual vapor pressure, and also wind velocity at height 9 meters. And the quotient can be estimated, Km quotient can be estimated using based on the type of water body that is there. So the next empirical method is Rover's formula proposed in 1931. Okay. Here we will calculate lake evaporation rate is equal to 0.771. So 1.465 minus 0.000 732 P naught plus 0.44 plus 0.0733 mu naught into EW minus EA. So here we have discussed that EW is saturated vapor pressure at water temperature, EA is actual vapor pressure, and U naught is wind velocity at 0.6 meter height. Okay, and P naught is mean barometric pressure in millimeter H. Okay. So in evaporation, we have discussed about what is evaporation and what are the factors that affect evaporation. Also, we have tried to measure the evaporation using the evaporation pans. And to obtain lake evaporation, we are multiplying the pan evaporation with pan quotient. Then we can use water budget equation also to calculate the evaporation that occurs within the catchment. And when we go for empirical formula, we have two types of formulas that I have discussed, Mayer's formula and Rowe's formula. Using these two, we can estimate the amount of evaporation that is occurring, because here in this empirical formula we only need minimum data like the temperature, that is temperature in the day, that particular day, and also wind velocity. Using that we can estimate the evaporation rate. But when you go for water budget equation, we need to have the inflow term, precipitation, outflow, seepage, and change in water storage. If there is any error in these terms, there will be an error associated with evaporation as well. Right. So now let's discuss some of the questions related to evaporation. So the first question is, evaporation term can be neglected in which of the following hydrological models? Okay, first one is event based. First is event based model, continuous model, option A and B, and option D, none. So the answer is event based model. In event based model, we can neglect evaporation term as we have discussed before, and in continuous model, we should not ignore evaporation term. So the next question is, how does soluble salts affect evaporation? Higher concentration of soluble salts increase evaporation, or the second option is higher concentration of soluble salts decrease evaporation. The third option is concentration of soluble salts doesn't affect evaporation. So as we have discussed, like if the concentration of soluble salts increases, the vapor pressure decreases for the liquid. So the evaporation rate decreases. So the next question is, which surface type generally has a higher evaporation rate? So first option is forested areas. Second option, concrete surface. Third option, wetlands. Fourth option is snow-covered surfaces. So the answer is concrete surfaces. Okay. So now the next question is, the pan factor used in the pan evaporation method is dependent on option E, season, B, location, option C, both, and option D, none. So the answer is option C, both. Whenever we are taking pan evaporation or pan factor, there is a range of pan factor that is mentioned in the table. Okay. So based on the season and location of the evaporation pan, we will decide the pan factor for that particular season and location and use it for the further calculation. Okay. So now let's solve the problem using Rover's formula. Calculate the daily evaporation rate for a open water surface given an atmospheric pressure of 760 mm of Hg and wind speed is 15 km per hour at 0 0.6 meter above the water surface. Saturation vapor pressure of 20 to 25 mm of Hg and actual vapor pressure is 15 mm of Hg. Okay. So the Rohr's formula is EL is equal to 65. This I have already discussed before. Okay. I'm just writing the formula. So here let's see what all terms they have given. So they have given the barometric pressure is 760 mm per Hg. Sorry, 760 mm Hg. And next, here U naught represent the wind velocity at height 0 0.6 meters, which is 15 kilometer per hour. And EW is the saturated vapor pressure, that is 25. Also actual vapor pressure they have given, right? So once we calculate it using calculator, so for me the answer is coming around 16.095 mm per day. So the answer is this. Okay. So now coming to next question. We have a Class A evaporation pan that is installed at the bank of reservoir. The water surface, the water, sur, the water surface area on a particular day is 50 hectares, and the recorded evaporation loss from the pan is nearly 2 centimeters. What is the anticipated evaporation loss from the reservoir of that day? So we have seen that actual evaporation is equal to pan coefficient into pan evaporation, right? So for class A pan, we have a pan coefficient of value 0.7. The average value I am considering for this problem, it was given 0.7 into. So now when we are calculating the evaporation, we know that 2 centimeters has occurred, right? So now I am multiplying with area of the reservoir to get the volume. Or so, okay. So they have given area is 50 hectares. That means 50 into 10 power 4 meter square into the pan evaporation value is 2 centimeters. That is 0.02. Okay. So once you calculate that, value you will be getting is 7,000 meter cube per day. Right. So first you can either solve like this or you can solve that E equal to pan coefficient into first pan evaporation, that is 0.02 meters. So from this you will have 0.014 meters evaporated in a day. So once to convert into volume term, we have to multiply with area. So the area of the reservoir is given as 50 hectares. When to convert it into meter square, we have to multiply by 10 power 4. So once you solve that, even then you will get 7,000 meter cube per day as answer. Okay. So the next question is calculate the actual vapor pressure in mmHg at 25. Sorry, it's not actual vapor pressure, it's saturated vapor pressure at 25 degrees Celsius. Okay, so we have talked that saturated vapor pressure is equal to 4.584 into e power 17.27 into T by 237.3 plus T. Here T is in degrees Celsius. So directly when if you substitute the values of temperature 17.27 into 25 by 237.3 plus 25. So once you solve it using calculator, the answer is 23.77 mmHg. Okay. So till now we have discussed about three types of abstractions that occurs in a hydrological cycle. First is interception. What are the types of interception? How they are estimated? And then we have talked about depression storage, how to estimate depression storage loss. And then we have talked about evaporation, what are the factors that affect evaporation, and what are the methods we can use to estimate evaporation, like empirical method or by experiment, like by taking field measurements using pan evaporation, and then evaporation using evaporation pans, and also using water budget. So now let's talk about evapotranspiration. Okay, so if we break the term itself, we can see that evapotranspiration is a combination of evaporation and transpiration. So both of these together combined, we call it as evapotranspiration. Okay, so generally the evaporation will occur from the soil surface or from the vegetation surface. Okay, but the transpiration will occur from the stomata of the leaves, or like the canopy of the trees or leaves. Okay, so evaporation occurs from water surface, soil surface. Transpiration will occur from canopy of trees or plants. Okay, so how do we define transpiration is that the transpiration is defined as the metabolism by which the plants utilize water for their metabolism and growth. So transpiration is a process by which plants utilize water for their metabolism and growth. Okay, so how does this transpiration occur? The roots will take the water from the soil, and this water will get transported to the stomata of the leaves, and then from there the transpiration will occur. So we can measure transpiration using phytometer used to measure transpiration. Okay. So in this, how do we measure transpiration is that we will uh, grow plants in large vessels and then we will calculate the weight before and after the test. Okay. So by this we will know the amount of water that got transpired from the plant system. Also here in evapotranspiration we have a lot of terms that we need to keep in mind. First one is potential evapotranspiration. So in potential evapotranspiration, what does it define is that the amount of water that could get evaporated and transpired by a specific crop, soil and ecosystem if there is sufficient water available. Okay. So if the water is sufficiently available, the total amount of the maximum amount of evapotranspiration that can occur in a particular crop and soil type is called as potential evapotranspiration. Okay. Mm. So this is the maximum evapotranspiration that can occur. Okay. So then we also have a term actual evapotranspiration. So when the water is not sufficient, then whatever the evapotranspiration that is occurring in that particular area, it is called as actual evapotranspiration. This is the real amount of water lost. Water lost by evapotranspiration when sufficient water is not available. So always AET is referred as actual evapotranspiration and PET is referred as potential evapotranspiration. So always AET will be less than or equal to PET. So if we have sufficient water conditions, then the real amount of water lost by ET is equal to PET. Okay. So that's why we have less than or equal to term. Then we have one more term, reference evapotranspiration. This is okay. So this is the rate of evaporation that occurs in the standardized reference system. So this will be used for comparison purpose. Suppose for in this reference case, we have a short grown grass, green grass, which serves as an um, benchmark for the other type of vegetation type. Okay. So we have short grass grown with an crop height of 0.12 meters and surface albedo of 0.23. This is considered as our reference crop. Okay. So the whatever evaporation that evapotranspiration that occurs in this reference setup is called as reference evapotranspiration. Rate of evapotranspiration in a standardize in a standard crop setup is called as reference evapotranspiration. Okay. So also we have one more term called as crop evapotranspiration. So as you can see here that in first place when we have a standard reference crop and this climate condition, whatever evapotranspiration that is occurring is referred to as reference evapotranspiration. So, but that's not what happens in real case. We have different types of crops like sugarcane, rice, etc. Right? So, the evapotranspiration ET that occurs in this condition will be different. So that's why what we have to do is we have to multiply with a correction factor, crop correction factor, to get the amount of ET that occurs in a specified crop. Okay, that is termed as crop evaporation. So, crop evaporation is termed as water required by a specific crop under given environmental conditions. So, this crop factor will change based on the type of crop that exists in the field. Okay. So that's why ETC is equal to crop quotient into ET naught. Hmm. So now here what we are doing is we have another term called stress or reduction quotient. Okay. When we have this stress non-standard conditions for water or environment, then we will multiply with Ks. When we have well water, like sufficient amount of water available in that in a particular crop, then we only have to multiply with Kc. Okay, to reference crop evapotranspiration. Then we will get crop evapotranspiration. But when we don't have sufficient amount of water or it is not well watered, then there will be an water stress that occurs in the field. So that's why what we will do is we will multiply this reference evapotranspiration with Ks and also crop quotient to get crop quotient adjusted. Okay. So is this clear? Like when do we multiply crop quotient and when do we multiply crop quotient and also stress quotient is? I hope it's clear. So ETC adjusted is equal to Ks into Kc into ET naught. Okay. So now let's look into the factors affecting evapotranspiration. Okay. Similar to evaporation, we have different factors. Like first one, we will talk about temperature. It's clear that if the temperature is high, the evapotranspiration rate is higher. Okay. Then humidity. So if the water content in the air is high, then the evaporation decreases. That's why the evapotranspiration also decreases. Okay. Then wind speed. So if we have high wind speed, the water molecules and the water bodies, everything get drifted away. So the vapor pressure will drop down, and to maintain the vapor pressure, again the water will get evaporated. So since the evaporation rate increases, we will also in turn will lead to increase in evapotranspiration. Okay. Next is solar radiation. If we have high intensity of solar radiation, then the evapotranspiration also increases. Okay. Then we have vegetation and plant characteristics. Sorry. So based on the type of vegetation, stage of the growth, health, size, and different factors, the evapotranspiration rate will change. Okay. So, and also there are other factors like altitude. If the altitude increases, evapotranspiration decreases. And based on if the climate and weather conditions are hot and dry, then ET increases. If they are cool and winter, then the ET will decrease. Also, because of soil moisture, if the soil moisture content is more, then we have that. If it is fully saturated, only the maximum amount of ET that can happen is PET. So it can't happen more than that, right? So that is one more factor that affects the evapotranspiration. So now let's look into how to estimate the evapotranspiration. So we have like instruments to measure it. First main instrument that we use is lysimeter to measure the evapotranspiration. Okay, so we can use catchment water balance, and this how do we estimate evapotranspiration? We need to have all these variable precipitation, change in storage term, runoff, and groundwater recharge. Using these terms, by subtracting these terms from precipitation, we can estimate evapotranspiration. Precipitation, change in storage, runoff, groundwater recharge. So we also have more than 30 hydrometeorological equations as well. From among that, we'll just discuss few of them that were highlighted in the lecture. So first one is Conway equation. It's an empirical equation proposed in 1948. Here it is calculated by 2.54 into K into F. So this K is empirical quotient which will depend on crop and the stage of the growth. Okay. Empirical quotient. And F is the sum of monthly consumptive use factors for the period, and it is calculated by using these terms like monthly percentage of annual daytime hours and also monthly mean temperature. This is monthly mean temperature. This is percentage daylight hours. Okay. Using that, we will calculate the consumptive use in monthly scale. Okay. Also next we have Blaney cradle method. In this, we will use this formula to estimate a reference crop evapotranspiration using the terms mean daily percentage of daylight hours P naught P into 0.46 mean daily temperature plus 8. Okay, we use reference evapotranspiration. Okay, then we have main important method, Penman method. So in this we are estimating potential evapotranspiration using this method. We have lot of terms in this equation. So when you are trying to use this equation, make sure that you calculate all the terms and all the terms are, please make sure that all the terms have correct units as well. Okay. So here the delta term represents the slope of saturation vapor pressure curve. Units are kilopascals per degree Celsius, and Rn is net radiation at surface. Units are million joules per meter square into day. Okay, and mine is psychrometric constant. It's a kilopascal per. So make sure all these terms are in this corresponding units whenever you are applying the Penman method. Okay. So we have also another term, latent heat of vapor pressure, vaporization. Okay. And the D in the equation represents vapor pressure deficit. We have already seen that EW minus EA. The units are kilopascal. And FU is wind function. Okay. FU is equal to 1 plus 0.563 into U. Here U is wind velocity at 2 meters height. Then we have FAO 56 Penman one-tenth method. The equation is you can see that the terms are almost similar to whatever Penman has proposed, but the main difference is in this we have a term called G. This G is represented to ground heat flux. This was missing in Penman method, and here also we have one more term T, uh, which is the mean daily air temperature. Okay. And the last one more method we have to measure evapotranspiration. So in this basically we will be using it to calculate reference evaporation. Reference evapotranspiration. Whenever I am using ET naught, it's reference evapotranspiration. Okay. So the equation goes like this. So here this is mean temperature in degrees Celsius. This is difference between maximum temperature and minimum temperature in a day. And this represents the extraterrestrial radiation, okay, in watt per meter square. So these are the methods that we use for calculating evapotranspiration. And why do we need this evapotranspiration estimates? Because we, based on that, we can understand how frequently we can irrigate, how much of irrigation we have to do, and all these terms will be known using by measuring the evapotranspiration. Okay, now let's look into few questions related to evapotranspiration. So first question is Penman's evapotranspiration equation is based on water budget method, energy balance method, mass transfer, and fourth option is energy balance and mass transfer method. So the option is energy transfer and mass transfer, sorry, energy balance and mass transfer approach. Okay, so what instrument is commonly used to measure transpiration from plants? So we have discussed that it is phytometer. And then we have one more problem where we will be calculating evapotranspiration using water budget equation. So here we can see that they have given terms like precipitation, stream flow, change in storage, and groundwater recharge. So from water balance equation, evapotranspiration is equal to P minus Q minus delta S minus groundwater recharge, right? So just make sure all these terms are in same units. We can see that all the terms are in mm per year unit. So I don't have to change them into common units, right? So simple calculation. The answer will be 800 per year. Okay. So now here I'm asking to calculate the evapotranspiration using FAO Penman Monnet method. Okay, so the equation for that is Et naught equal to 0.408 to delta Rn minus G plus gamma into 900 by T plus 273 U2 into Es minus E by delta plus gamma into 1 plus. So here we have given all the values for each term. So you have to make sure that they are in the correct units that I have mentioned earlier. Okay. So delta is 0.189 into Rn is 12 minus ground flux is 0.5 plus 0.067 into 900 by 25 plus 273 into 3.17 minus 1.8. ES and EW are given. Okay. So just make sure you are inserting the values correctly in the equation. Okay. Point U2 is wind velocity at 2 meter height. It is 2 meter per second. So upon calculation, I got value around 4.77 mm per day. Okay. So now let's look into the main abstraction that occurs in hydrological process, that is infiltration. So infiltration is defined as movement of water through soil surface into soil profile. Okay. So this is the major uh, source for abstraction that occurs as we have done, and also it will affect the distribution, timing and magnitude of surface runoff, subsurface flow, and also the storage of the water within the catchment. Okay, so here so we can see that when there is water on the surface, the condition is called as ponding surface, and the amount of water that gets seeped into the soil, we can see there is a profile for it. Okay, so we can see there is a sharp change in the water level. uh, f- we can see that the water is 100% saturated for this small depth. This is called as saturation zone, and there is a sharp change in the water content, that is transition zone. And there is one more zone where you can see that the water content is maintained constant for a huge depth. Okay, this is called as transition zone. And we have a zone where there is, till here there is water content, and after that there is no water content. Okay, so the area in between these two is called as wetting zone. Okay, and this surface which exposes the wetting and non-wetting zones is called as wetting front. Okay, so this is the basic soil water content profile in the soil. And generally, we will use, how do we measure infiltration is we will have instruments like, first one is double ring infiltrometer or flooding type, where we have like two rings. Okay, so water is filled in both the rings. Basically, we have water in this so that no lateral flows in the subsurface will affect the infiltration that is occurring within this inner ring. Okay, so this is where within this inner ring only we will take the infiltration measurements. Okay. So, but the main problem with this double ring infiltrometer is that it cannot simulate the rainfall. So once the, because when the rainfall occurs, there is like soil erosion kind of thing will happen. So the infiltration will change. So that's the main disadvantage of this method. So we have one more instrument called rainfall simulator infiltrometer. Okay, this can simulate the rainfall, and by using this we can measure other terms also like surface runoff, and also soil erosion studies also we can do using rainfall simulator infiltrometer. Okay, and the main important term in infiltration is infiltration rate. So this accounts to rate at which water enters into the soil at it enters into the soil. Okay, rate at which water enters soil at its surface is called as infiltration rate. So generally we have a infiltration curve which is a plot between infiltration rate F to time. Okay. So initially we will consider that the amount of infiltration is maximum, the infiltration rate is maximum, and it is termed as initial infiltration rate F naught. And after some time, the infiltration rate becomes constant, and this is called as constant infiltration rate. So this is because if initially when the soil is dry, the amount of water that is entering the soil will be more highest, So we experience maximum infiltration rate, and then there will be resistance between the water flow, resistance that acts on the water flow. So the infiltration rate decreases. This curve is called as infiltration curve. Okay. So this is the F0 represent the maximum infiltration capacity of the soil, and FC is the constant infiltration capacity. Okay. So we have discussed about how to measure the infiltration using double ring method, double ring infiltration infiltrometer, and also rainfall simulator. Now we will talk about infiltration indices. First one we have phi index, which will calculate the average rainfall rate above which rainfall volume is equal to runoff volume. Okay, so suppose you remember hydrographs, it's a plot between rainfall intensity and time. We have bar plots. Okay, so suppose we say that phi index is this value. So what does it mean by that is that whatever rainfall above this line is called as rainfall excess. Okay, and this volume, this area will give us the runoff. Okay, so at this point, the phi index is the value that will make sure that excess rainfall will be equal to the storm runoff. Okay, so we have formula P equal to pi minus pi equal to P minus Q by TD. TD is the duration of excess rainfall. So here we can see that few bars are below this pi values. So these rainfall events we do not consider when we are calculating pi. So when you are calculating here, this P is also excess rainfall. So only this values, these bar values are considered in PE terms, and TD is the duration of excess rainfall. That is only this duration is the it represents the time where excess rainfall is occurring. Okay, and we have one more index, W index. So here in pi index we are not considering initial losses like interception, depression, storage, etc. So in W index we will consider that initial losses by TD. Okay, so generally we will notice that W index is always less than or equal to pi index. Okay. And now we have different models, empirical models, which can be used to estimate the infiltration values. Okay. So first one is Kotsiakov model, where cumulative infiltration depth is defined as A into T power B, and infiltration rate is AB into T power B minus 1. A and B are empirical parameters, and A value will be always greater than 0, and B value is always between 0 and 1. Okay, and also we have a condition here that if infiltration rate is 0 at time t equal to 0. Okay, and the second empirical method is modified Kotsiakov model, where cumulative infiltration depth is defined as A into e power, and we are including constant infiltration rate as well here. Okay. And similarly, by differentiating it, we can get infiltration rate as well. So this is the equation for that. So next we have semi-empirical model, that is Horton's model. So Horton basically assumed that the infiltration will exponentially decay. Infiltration rate will exponentially decay with time. Okay. So for that he has proposed this equation. This is initial infiltration rate and this is constant infiltration rate. Right. It's equal to f0 minus f e power minus k2. K is the decay constant. And cumulative infiltration depth is measured using this formula. So if you differentiate the cumulative infiltration term, then you will get infiltration rate. If you integrate the infiltration rate, you will get the cumulative infiltration rate. Here we are considering the condition where cumulative infiltration rate is 0 at time t equal to 0. Also, when you have like infiltration values measured, then instead of like it's very hard to estimate these terms when you fit an exponential curve, right? So we try to convert into linear term by taking natural logarithm. Okay. So when you plot it on a semi-log curve, t versus ln of f minus fc, you can see it will be a straight line with slope k, and this y-intercept will be ln of f naught minus fc. Okay. So, and also now we will talk about some physical models to estimate the infiltration rate. The first one is Greenamp model. So this is based on Darcy's law in uniform soil case, and also here we are assuming that there will be negligible ponding depth. Okay, and the equation for that is f equal to one second. F equal to k into okay. So infiltration rate is a function of cumulative infiltration. Also, size, suction head, K is decay factor, delta theta is change in water content, etc. Okay, and then we have another physical Philip two term model. The equation for that is cumulative infiltration depth is function of sorptivity and time. Okay, so sorptivity S is defined as a measure of capacity of medium to absorb or dissolve liquid by capillarity. Okay, so this can be calculated by using this formula. Okay, next we have one more method, Richard's equation. So it is based on one-dimensional continuity equation and also Darcy's law. And here they consider that as hydraulic conductivity of the soil increases, the moisture content increases, and if when the hydraulic conductivity decreases, it decreases with suction head. Okay. and the formula is equal to dou by dou z into, so here this term represents the soil water diffusivity. D of theta is equal to hydraulic conductivity into change in suction head. Okay. So these are the equations that that are involved in infiltration, which is a very lot of equations that I have talked about. So due to limitation of time, I just skip the introduction of this. You can see all these methods have been already discussed in week 2 lecture. And basically, so in this infiltration, we have talked about what is infiltration and how the infiltration rate changes with time. Also, the infiltration, how do we measure infiltration using the instruments like rainfall simulator, infiltrometer, also double ring infiltrometer, and the indices involved in the infiltration, and the empirical, semi-empirical, and physical models which can be used to estimate the infiltration rates. Okay, now let's look into the problems. So the first question is, infiltration losses are the highest in the beginning of the storm, middle of the storm, towards the end of the rainstorm, or the fourth option is can be any time during the event. So we have seen the infiltration curve that it exponentially decays. So we can see that at beginning of the storm, the infiltration loss is highest. Okay. So what are the limitations of Conseco equation? Okay. So it fails at t equal to 0 time, it fails at t equal to infinity, and it fails. Third option is it fails at both A and B conditions. Fourth option is D, none of the above. So if you check the week 2 lecture, you can see that Conseco equations fail at both time t equal to 0 and t equal to infinity. So the next question is, which is not a disadvantage of double ring infiltrometer? So the first option is outer cylinder is used as a buffer to check lateral flows of water. So the second, so we are actually using outer ring to check the lateral flow. Okay, so that's not a disadvantage. And the next option is water level fall in the inner cylinder with time is measured. Yes, this is also correct. Third option is raindrop impact effect is not simulated. Yeah, we can. It's raindrop impact is not simulated in double ring. That's why we are going to rainfall simulator in infiltrometer. And the fourth option is D, none of the above. So which is not a disadvantage. So these two are the advantages of the double ring infiltrometer. So it will be A and B. So next we have a problem. So the rate of rainfall for successive 30-minute period of a 4-hour duration storms are given. Taking pi index as 5 centimeter per hour, we have to calculate the total storm runoff. So when first thing is that we have to plot the hydrographs, which is a plot between rainfall intensity and time. We can see that the rainfall intensity is given like 3.5, 4.5, 5.6, 8.7, 7.8, 6.4 by 4. So suppose 5 centimeter per hour is here, the pi index value. Okay. All these are contributing for excess rainfall. That is 5, 5.6, 8.5, 7.8 and 6.4, where the time duration is 30 minutes. That is half an hour duration. Right. So when this above area will give us total storm runoff. Okay, so how do we calculate that? We have to find the area of those bars. Okay, total storm runoff is equal to, so the bar above 5 centimeter per hour should be considered. Okay, so it is 5.6 minus 5 into time is half an hour plus 8.5 minus 5 into half an hour plus 7.5 into minus 5 into half. Last bar 6.4 minus 5. So it is 0.3 plus 1.75 plus so once you add this, it will come around 4.15 centimeters. So this 4.15 centimeter is the area of these bars above 5 centimeter per hour, above this 5 index. Okay, so this will represent the total storm runoff. Okay, so now coming to last question. Have to use Horton's infiltration model to calculate the infiltration rate and also the cumulative infiltration depth when we have the initial infiltration rate F naught given and the soil reaches a steady infiltration rate F0, that is constant infiltration rate Fc, and we have a decay constant K equal to 0.15 per hour based on previous studies. So we know the formula for infiltration rate from Horton's is Ft equal to Fc plus F naught minus Fc into e power minus K2, right? So for first hour, what we have to do is replace this time with 1 hour. Okay. So here Fc we know 4. F naught is 12 minus 4 into e power minus K into T is 1 hour. Okay. So when you calculated the infiltration rate after 1 hour is 10.89 centimeter per hour. And similarly for second and fourth hour, how do we calculate is like we will replace the time term with the with second hour. In second hour T will be 2 hours and in fourth hour T will be 4 hours. Okay. And similarly we will calculate the infiltration rate at time equal to 2 hours. We have 9.93 centimeter per hour as the value. And at fourth hour, we have 8.39 centimeter per hour. So we can see that as the time increases, the infiltration rate is decreasing from these values. Okay. Also, we know that cumulative infiltration depth is FCT plus F naught minus FC into C by K into 1 minus e power minus kt. Okay, so this is the cumulative infiltration term that we have. So in this term also we know Fc, F naught and K values which are fixed at different duration, and when the duration is changing for time t equal to 1 hour, that we will replace t term with 1, and at time equal to 2 hours we will replace t equal to 2. And similarly at a time t equal to 4 hours we will replace the t equal to 4. We will replace the t term with value 4. Okay. And we will calculate at each term the infiltration depth at each duration. Okay. At t equal to 1, the infiltration depth is 11.44 centimeter after calculation. Similarly, at time equal to 2 hours, the infiltration depth is 21.76 centimeter. and at time t equal to 4 hours, the infiltration depth is 40.08. So we can see that as time increases, the infiltration depth is increasing, but as time increases, the infiltration rate is decreasing. Okay, so this you should keep in note that with the time, the infiltration rate decreases, and with time, infiltration depth increases. Okay, and becomes constant after some point. Okay, so that is our last question. And if you have any other questions, you can raise the hand or ask any questions related to abstractions topic.